So we have talked about the local density approximation, which is the simplest possible approximation you can make to basically for the exchange correlation part, which is the unknown in DFT, right? Now, obviously, we don't stop there, right? So there are limitations in DFT. So we are going to try to improve on exchange correlation, our exchange correlation functional by making more and more sophisticated approximations, right? Now, what is the next step after a local approximation, right? In the local approximation, I'm just assuming that my exchange correlation energy is related to my density at every single point in space, right? So the next obvious extension to LDA is basically to add a gradient, right? So instead of thinking of my exchange correlation energy as just being related to the local density, I'm going to assume that my exchange correlation energy is a function of not just my local density, but also the gradient of the density at every single point, okay? And that leads to what is called the generalized gradient approximation, okay, or GGA, right? Now, so in the GGA approximation, your exchange correlation energy is not just a function of your spin up and spin down densities, but also the gradient of your spin up and spin down electron densities, okay? Now, there is no one single GGA, okay, so there have been many different forms of GGA developed by various developers over the years, okay? And these are just, this slide shows you some of the more commonly used GGAs out there, okay? There's the BLIP, which is developed by Exelbeck in 1988, and this is based on the energy density of atoms. So it is a one-parameter exchange together with correlation parameterized by Li, Yang, and Parr. Okay. The next GGA that has been still even today is still widely used is called the PW91. 91 stands for the year, okay, that it was published. Okay. PW stands for Purdue-Wang. Okay, and so PW91 is still quite commonly used today, but by far the most popular GGA that is used in most works out there that you see today is what is called the PBE functional, and the PBE is basically just the initials of the three scientists who developed this functional, Purdue, Burke, and Erzenhoff, and this was developed in 1996, is essentially just a reparameterization and simplification of the PW91 functional, okay? Now, this is still very widely used today, okay? There have been further improvements on the PBE, okay? So, for example, in 1999, there's this thing called the revised PBE, which improves the surface energetics predictions of your standard PBE functional. There's something called PBE Sol, which was developed in 2008, which is a revised PBE for solids, which tend to give you slightly better lattice parameters compared to your standard PBE functional. Okay. Now, let us look at what the performance of your GGA functional is. Okay. So one of the advantages of the GGA is that it tends to correct the overbinding tendency of your local density approximation. Okay, so if you recall this chart that we showed earlier, the black line is basically your LDA predictions, and this zero line essentially is the zero error line with for your lattice parameter predictions, and you can see that LDA consistently underestimates your lattice parameters, right? However, if you look at the GGA functional, okay, so there are a few GGAs here. There is the green line is PBE. PBE tends to slightly underbind. In other words, it tends to slightly overestimate the lattice parameters of your experimental lattice parameters. Okay. Nevertheless, the error is still much smaller. And of course, the newer versions of PBE, like PBE SO, so this is this dark blue line over here, and you see that the PBE SO does even better than LDA and PBE. It's actually almost right on that 0 line over here, okay, on average. And so in general, the GGA tends to leads to better bond lengths, better lattice parameters, and not only that, it also leads to better atomization energies, and in general, your energetics are significantly improved relative to LDA, okay? Now, of course, in the GGA, we added the first derivative. There's no good reason why we can't add more derivatives, okay? You can do that, of course. So things like what are called the meta-GGA functionals, they add things like the second derivative of the density to parameterize the exchange correlation energy, okay? So an example of this functional is called the TPSS functional, okay? And so there are a lot of other meta-GGA functionals out there, okay? So the issue with going for higher and higher order derivatives is always that your computational costs do increase somewhat, and in some cases, the stability of your convergence and calculations also tend to be compromised somewhat, which is why, in general, the meta-GGAs are still not as popular as just using standard GGA, okay? Okay, now, there's a variant of your standard LDA and GGA functionals, or even meta-GGA functionals, and these are what are called the orbital-dependent methods, okay? In general, these are denoted using the notation of DFT plus U. DFT plus U simply means that I'm using density functional theory with an addition of a Hubbard U parameter. So why do we want to do this, right? The problem with a local density based approach like LDA or GGA is that they tend to over-delocalize your electrons, okay? What this simply means is that even though you may have a transition metal where your electrons are fairly strongly localized to the d orbitals, the LDA and GGA approach tends to over-delocalize them. So in other words, you have partial occupancies in your d orbitals, right? And that actually doesn't happen in reality, okay? So in most materials, your d electrons are actually fairly well localized, okay? So in the DFT plus U method, basically what you do is that you add a Hubbard-like term. The Hubbard-like term essentially is this penalty term right here, okay? And what this penalty term does is that it penalizes partial occupancies of the orbitals that you specify, okay? So typically we will specify that we want to penalize partial occupancies in the d orbitals, for example. And in doing so, what this means is that the convergence of your energy will go towards a state where you actually have fully integer occupations in your d orbitals, okay? So the only problem with this approach is, of course, that now you actually have to specify what this U parameter is. This U parameter essentially is the strength of the penalty term that you apply to your standard GGA energy, standard DFT energy, okay? And you basically have to get your U value using some empirical approach, okay? So there are a few methods in which you can get U values, okay? One is you can either fit it yourself. There is something called the linear response approach, where you can essentially do a self-consistent determination of what a good U value for a particular system is supposed to be, okay? More typically, people, while this is obviously a much more rigorous way of getting a U value, most people actually do fit U values by fitting to experimental data, okay? So for example, if you are mostly interested in the electronic structure properties of the material, and you're just interested in, for example, getting the band gap right for your solar material or whatever material you're interested in, then what you will do is that you will fit the U value such that you actually get the correct band gap for your material. Okay? If you are not interested in trying to fit U values yourself, there are already well-tested values of U values in the literature where people have already done the fitting for you. For example, the materials project, which I'm involved in, we actually fitted the U values for a large number of transition metals to reproduce like the formation energies of these transition metals, okay? Or rather the oxidation energies of these transition metals, right? So you can of course take these values as a starting point and do your calculations. Obviously, when you interpret your calculations, you still need to be careful about how you interpret them, okay? All right, now the last type of functional that I'm going to talk about, exchange correlation functionals that I'm going to talk about are what are called hybrids, right? So hybrids are essentially functionals that combine your semi-local DFT with the Hartree-Fock approach, okay? So this is basically the chimera from God of War, okay? So when I was still a carefree grad student, this was basically what I played all day when I'm not doing research, okay? So when you combine Hartree-Fock and the density functional theory functionals, one question is, of course, what's the ratio of the Hartree-Fock and DFT? In what ratio should you be combining your Hartree-Fock and DFT, right? So the rationale for hybrids is quite simple. Semi-local DFT like LDA and GGA, they tend to suffer from what is called the self-interaction error. In other words, you have that interaction of an electron which is with itself, which is actually not completely cancelled when you are using an approximate exchange correlation functional like LDA or GGA, right? So if you look at this electron-electron interaction term, there is this integral of the two charge densities, and this includes the case where I is equals to J, right? And that is an electron-electron self-interaction. Now, of course, your exchange correlation functional do cancel out this part. It is supposed to cancel out this part to some extent, but it only cancels it out in the limit of your homogeneous electron gas, right? So in most systems, you don't actually have complete cancellation, right? Now, the difference is, of course, that the Hartree-Fock approach actually cancels out this self-interaction by construction, right? So if you recall, the way that we went through the whole Hartree-Fock derivation is such that we already have this cancellation term that is built into the Hartree-Fock formalism, right? So we actually have exact cancellation of this self-interaction error, okay? At least for the exchange part. So basically, the rationale is then to combine the two, all right? So there's this very popular hybrid functional called B3-lip. It stands for back 3-parameter Li-Yang Pa. 3 parameter simply means that I actually have 3 mixing parameters for my mixing of my Hartree-Fock with my DFT functionals, okay? So the exchange correlation energy of your B3-lip functional is given by the exchange energy of your LDA plus A naught times the Hartree-Fock minus the LDA exchange energy plus AX, which is your GG multiplied by the difference between your GGA and LDA exchange energy, plus this correction, plus essentially your GGA correlation energy, okay? So the parameters like A naught and AX and AC, they are all fitted to reproduce the energetics of small molecules. So they have these values, okay? So this is just for you to, as a reference. Most of the time you don't even look at them, okay? the reason why B3-lip is so important is because it's arguably the most popular functional in quantum chemistry, right? You pick up any publication doing quantum chemistry calculation on molecules, the chances are more often than not that that paper is using the B3-lip functional, okay? If you recall, when I talk about the top 10 most cited papers in all of history, the paper that is defining the B3-lip functional is actually the 8th most cited paper in all fields, okay? So it was originally fitted to a set of atomization energies, ionization potentials, proton affinities, and total atomic energies. And it actually works surprisingly well across in a very general sense, okay? So obviously there are still instances where it fails, and it fails quite spectacularly, but for most general purposes, the B3-lip function actually works reasonably well, okay? Now, there is also a hybrid functional called PBE0, okay? It's actually a bit confusing, okay? I don't know why they name it PBE0, but PBE0 simply just takes the Hartree-Fock exchange energy, and then you add it to the PBE exchange energy, and you mix it in a ratio of 0.25 to 0.75, okay? The correlation energy still comes from your PBE functional, okay? Now, this is very often used for more accurate solid calculations of things like the electronic structure, okay? But more recently, this has given way to what is called the HSE functional. HSE stands for Hertz, Kucera, Unzenhoff, and it was developed in 2006. And the difference between HSE and PBE0 is basically just that there is this range parameter, okay? And the range parameter, essentially, what it does is to say that I'm going to only deal with this Hartree-Fock exchange part within a certain short range, okay? And I'm going to smoothly decrease that range down to 0 within some distance, okay? And the reason for doing this is to really just reduce the cost of your calculations, okay? Because in most cases, the exchange interactions is actually the range of your exchange interactions is not that long range, okay? So the HSE functional is basically what is called a screen hybrid functional, and it works remarkably well for most solids, okay? So nowadays, it's rare that you will try to use the PBE0 functional. Quite often, you will actually go with the HSE functional, okay? All right, just to show you whether hybrids work, okay, so one of the main reasons you want to go to hybrids is to essentially correct for that underestimation of the band gap by your semi-local functionals like LDA and GGA. And you'll see that here the HSE functional is this black square over here, and you can observe that essentially all your predicted band gaps of this whole series of materials, they actually fall fairly close to this one-to-one line, okay? While your LDA and PBE functionals, obviously, there's a significant underestimation, okay? So the hybrids also leads to much better predictions of your lattice parameters in most cases, okay? So if you look at this benchmarking that was done, you see that the mean absolute error in the LDA functional is about 5%. The mean absolute error in the PBE functional is, in this case, at least for this data set, is about 8%, but it is in the opposite direction from your LDA. While your HSE functional, the error is actually about less than 4%, okay? And the minimum and maximum errors are also more well-behaved in most cases, okay? All right. The other reason why you would want to use hybrids is especially in cases where the self-interaction error would manifest itself. And one of the most most important cases where this self-interaction error occurs is when you are calculating reaction energies, especially reaction energies involving change of oxidation state. Okay, so for example, there's this work that was done by Chevrier, and essentially he looked at the lithium intercalation potential of different lithium-ion battery cathode materials, and he calculated them using your GGA functional, your GGA plus U functional, and your HSE functional. Okay. Now, you'll see that the GGA functional significantly underestimates the voltage of your cathode material. Okay, and this is really mostly the result of your self-interaction error. Okay, so when your cathode material undergoes a lithium intercalation process, what is happening is that you have a change in the redox of your transition metal, right? So for example, your lithium cobalt oxide, it starts off as 3+, it will go to 4+, okay? And that is one of the situations where you actually have this manifestation of your self-interaction error. Now, if you use a U parameter, obviously you can get very good agreement with the experimental voltages. Okay, so this is not surprising, right? Because we fitted the U value to reproduce the oxidation energies. So the agreement with the experimental values is quite clear, right? Now, with the HSE functional, where there are no adjustable parameters, you see that you actually also get a very good agreement with the experimental predicted voltages. Okay. Now, you can also look at things like the formation energy of the oxides. Okay, so this essentially is a calculation of the formation energy of the oxides per O2 with the GGA and the HSE functionals. And again, what you see is that for the main group metals, there really isn't that much of a difference between the HSE and the GGA functionals, because in those cases, you don't have any localized electrons, okay? But once we look at the transition metal oxides, then this is where that HSE actually significantly outperforms the GGA functional in terms of predicting the oxidation energies of your transition metal oxide, okay? All right, so in the literature, you will often hear what is referred to, yeah, sure.
In the previous slide, yeah, I fail to understand, is the HSE doing much better than GGA, because they seem to, okay, the circle is the GGA.
Yeah, the circle is GGA, so the errors tend to be larger and it's also more spread out. And the squares are basically your HSE, and they are fairly close to the one-to-one line. Okay, of course they are not perfect, but they are fairly reasonable. Okay. All right. Now, when you read the literature, you will often encounter what is referred to as the Jacob's ladder of functionals. This simply is essentially a ladder of functionals in terms of the accuracy and also in terms of inverse cost. Okay, so at the bottom level of the functional world is basically your LDA, and then the next level up is GGA. Then you have your meta GGAs, and then you have what basically your hybrid methods with exact exchange, and then further up, you basically have exact exchange with partial exact correlation. And as you scale up, as you go up the ladder, essentially you get closer and closer to chemical accuracy in terms of your predictions. Okay, but of course, all this comes at a cost, right? Typically, as you go up the ladder, the more expensive the method is going to be, right? So, unfortunately, and is a fairly confusing world out there. Okay, so there are literally hundreds of different functionals that you will see. Okay, and this is actually fairly old. Okay, I haven't even included any of the newer functionals. Okay, so new functionals are being developed by people every year, every month. Okay, so you have functionals that include things like the van der Waals interactions. You have functionals that correct some specific error in your standard GGA, and so on and so forth, right? But here it just shows you essentially the size of the letter shows you how often that functional is being used in a publication, right? And it's no surprise B3lib is one of the most popular. It's less used for solids, it's mostly used in quantum chemistry, but because of the sheer volume of quantum chemistry paper, it is one of the most used functionals in the world. Okay, and then next level up, you have your PBE and local density approximation. LSDA just simply means local spin density approximation. It's just the local density approximation, but with spin polarization. Okay, and all the others that I'm not going to go into. Okay, so to answer the question of which function you should use, we go back to our trade-off trinity, which I talked about in our first lecture. It is always a trade-off between accuracy, cost, and system size that you want to simulate, right? And typically, you have to choose one or two of these things to get, okay? Now, as I mentioned before, because LDA overbinds, GGA and meta-GGA largely corrects that overbinding. So by default, I would say in most cases nowadays, if you are doing a DFT calculation, you would tend to just go straight to the GGA, okay? It is actually in very rare instances that you actually choose the LDA functional for any purpose, okay? Similarly, if you look at the cohesive energies, as I mentioned, because LDA tends to overbind, the cohesive energies are too high, okay? So in other words, are too low. In other words, the energy to separate something out to too low, meaning it's too negative, right? Because LDA tends to overbind, it means that the atoms are actually much more strongly bonded to each other than they should be, so they are more negative, right? And again, GGA does much better compared to LDA in terms of predicting things like the cohesive energy, okay? So similarly for bond lengths, if you compare the GGA functionals, the errors are definitely much smaller compared to something like the LDA functional, okay? And again, this is a reason why you would generally go for your GGA functional, okay? So the conclusion, LDA almost always underpredicts the bond lengths, lattice parameters, and overbinds. GGA error is smaller. It is a bit less systematic. It tends to underbind, but it is a bit less systematic. And the error in GGA in a lot of instances is actually less than 1%. So the conclusion is that you usually don't go for your LDA, okay? And the reason is also because the computational costs between LDA and GGA are actually fairly similar, right? So you are not gaining a lot of computational efficiency by using LDA, okay? All right, just to show you what you can do with some of the GGA calculations. So one of the key purposes of doing DFT calculations is sometimes to determine what is the lowest energy structure of for a given composition, right? So we can benchmark this using all the elemental phases in the periodic table, right? And if you look at the atomic energy that you calculate with your GGA PBE functional, is around negative 1,894. And if you look at the FCC energy phase, is negative 1,894.7325. And for the BCC phase of vanadium, you basically get the same factor before the decimal point, and even the first decimal point is still the same, and it's only the last 3 digits that are much smaller, okay? So if you want to calculate something like the cohesive energy, it's basically the energy of your BCC phase, subtract out the atomic energy, and you get a value of 0.638 Riebeck, okay? And you can see that this is only about 0.03% of your total energy, right? Now, if we are looking at the difference between something like the BCC and FCC phase of vanadium, the difference in energy is just 0.02 ripple, which is an even smaller percentage of your total energy, okay? It's just 0.001%. And of course, things like mixing energy, if you are calculating things like what's the energy to mix two metals together, those tends to be 10 to the power minus 6 of your total energy, okay? And what this shows you is that in many cases, your density functional theory, doing density functional theory calculations to determine energy differences is sort of like you're weighing a huge cargo ship and you're trying to determine the weight of a human on board, right? And you're essentially weighing the cargo ship with the human on board and weighing the cargo ship without a human on board and taking a difference between the weight between the two, okay? So it is a very sensitive calculation, okay? So that is why convergence of those calculations are actually fairly important, okay? Now, this is actually a benchmark that was done by Kuchurov together with Gert Sieder and Zikui Liu. And what this shows essentially is that even though if you can look at the sensitivity, how small a percentage that energy difference is with respect to the total energy, in most cases, DFT actually gets you the correct phase for your elemental structures, okay? So those in green are basically those which actually have a correct energy difference between your BCC and FCC phase, and the red ones are essentially those that have an incorrect BCC, FCC energy difference, okay? And these are based on structures at standard temperature and pressure, right? And you'll see that actually in most cases, DFT, GGA actually gets it correct. In those cases that they are wrong, there are sometimes the energy difference are very, very small, okay? So it's not that the DFT is definitely incorrect. It may also be because that at 0K, you actually have a different structure that is stable, okay? Now, from your DFT calculations, you can also do things like determine the magnetism of your structures. If you look at this table that is obtained from this paper by Lei Wang, you can see that basically, in general, the predicted magnetic moments on all your transition metals, they are actually in fairly good agreement with the experimentally measured magnetic moments for each of your transition metals, okay? Especially if you make sure that your orbitals are correctly localized, for example, using the GGA plus U method, okay? All right. Now, what about molecules? Okay, so in terms of, in molecules, very often we benchmark the performance of functionals or quantum chemistry methods using things like atomization energies, ionization energies, and electron affinities. And this is basically a benchmark that was carried out over a G2 test set of molecules. So this is basically a very, very large test set that people use quite often to benchmark quantum chemistry methods. So if you look at the table, just a note that the PBE1, PBE in this table basically just refers to the PBE functional, okay? And you will see that essentially the atomization energies are actually pretty good, right? So you have the PBE1, PBE functional, you get a mean absolute error across the G2 test set of about 4.8, I think it is kilocals per mole, yes. And this compares quite favorably to something like B3 which gives me about 3.1 kilocals per mole, okay? Similarly, for the ionization potential, GGA, the PBE functional actually also does reasonably well, and also for electron affinities, it does slightly worse, but it is still pretty good, okay? You can also look at the reaction energies, okay? So here the reaction energies for different molecules, I what I've highlighted here are the key rows in the table that I want you to focus on. Okay, so if you recall, your Hartree-Fock method tends to get reaction energies terribly wrong. So if you look at the mean absolute error in your reaction energies with your Hartree-Fock method is about 150 kilocals per mole. MP2, which of course takes into account electron correlation to some extent, brings that down to about 24 kilocals per mole, right? And obviously you can go to more and more accurate methods, and but let us look at what you get with your PBE and B3lib functionals, right? So the PBE functional gets an error of about 12.1 kilocals per mole. Okay, so quite good, right? So, and B3lib does even better. You can actually get reaction energies to about a mean absolute error of about 7.2 kilocals per mole, right? So the broad conclusions is basically GGA is better than LDA, and hybrids are actually quite efficient. They actually get good accuracy and compared to highly correlated methods, right? So just look at the B3lib error is 7.2 kilocals per mole, okay? And this is the reason why the B3lib functional is so popular with a lot of quantum chemistry publications, because it gets surprisingly good answers, right? Even though there may be instances where it can fail quite badly, right? If you look at this reaction set 3, you can check out the B3lib numbers again. B3lib 8.6 kilocals per mole, and something like MP2, you are looking at 9.6, right? And so B3lib still does better than even something like MP2, and B3lib can be significantly cheaper than MP2 to calculate, okay? All right. In some instances, there are some problems with different functionals, okay? So especially in terms of, for example, the GGA functional, or it doesn't matter, actually in most cases, things like your semi-local DFT functionals, they tend to get certain binding energies significantly wrong, okay? So one classic case is the oxidation energies for transition metals. So what you will see is that even with the GGA plus U method, you actually see that there's this big gap between the experimental formation enthalpy for your different oxides versus the calculated formation enthalpy of your different oxides. And this shift, this error shift, is really due to the fact that GGA actually calculates the binding energy of your O2 molecule wrong, right? And this is something that you can fix fairly simply. It's somewhat empirical. Basically, what you do is that you basically take the oxidation energies of your main group metals, which are essentially not where you don't really need your Hubbard U parameter, and you basically draw a line and you basically fit this gap, and that gap gives you your 1.36 EV correction to your formation enthalpy. Okay. All right. If you know what you're doing, the results with your standard semi-local DFT can be pretty good, right? So this is actually a high throughput analysis that I did for different binary compounds in the materials project. Okay, so the materials project is this very large open database of computed properties of different materials, and what you see is that across all the different chemistries, we have formation enthalpies that are distributed around 0. So in other words, on average, the error is still 0, roughly 0. Okay, and in general, most of them are within, say, 30 kilojoules per mole or so. Okay, and that's actually fairly reasonable. Okay. This is true regardless of whether we are talking about oxides, which is of course the largest class of materials that is in the materials project, but also things like fluoride, chlorides, bromide, iodides, sulfides, phosphides, and nitrides. Okay. Okay. Obviously band gaps is still a problem. In LDA and GGA, they are very bad. They tend to be severely underestimated. Hybrids, they definitely fare much better, okay? So you definitely get much more accurate band gaps with hybrid functionals like HSE or the B3 lead functional. There have been new functionals and methods that have been developed to deal with this problem. For example, there's a functional called the GLLB functional that some people use to actually get more accurate band gaps. There's also something called delta SCF for solids. Basically, what this does is you, instead of doing just your calculating your band structure, you basically do a two-step calculation where you add or subtract a certain number of electrons from your system to basically take the energy difference between them to basically get your band gap, okay? And that generally also works much better than just a straight semi-local DFT band gap. Okay, with that, I covered all the exchange correlation, in general, the exchange correlation functionals that I wanted to cover. Any questions on this part before we move on to the next section?